So today's featured speaker is Dr. Eric Ford. He's a professor in Penn State's Department of Astronomy and Astrophysics, who is also affiliated with the Institute for Computational and Data Sciences. His research aims to understand the formation of planetary systems by applying modern statistical and computational methods to interpret extrasolar planet observations. So today, Dr. Ford's lecture will be entitled The Road to Characterizing Potentially Habitable Planets. So Dr. Ford, thank you so much for being here today, and we look forward to hearing more about this topic.
Thank you, Jessica, as well as Joel and Professor Ashtekar and Barbara Kennedy for all their work in making this event possible and helping get so many of you out here to participate in it. Thank you. Before we get started, I should say a little bit about why I think events like this are so great. Science is a long process. We start with an idea, we develop it, we ask for funding, we're told no, we try again, maybe 2 or 3 times. We get a grant to do some work. The university likes our press release, but we have nothing to say yet. Then we work on something for 3 years, 4 years, 5 years. We finally submit a paper. We get feedback, we revise, revise again. And finally a paper is published, and then the press wants to ask about it. By then we've moved on, we're kind of no longer enthused about it. And so events like this that ask us to share our science between the process of the inception of the project and the conclusion give a chance to share what we're doing now, what we're excited about, what the students are involved in. And so I like events like this in the middle, because that's where science really happens. What I'll be telling you about today is work that's at the intersection of a few different fields. This seminar series is emphasizing data sciences, prediction, statistical modeling, the computation that goes with them. And my own application area, exoplanets, is the focus of Penn State Center for Exoplanets and Habitable Worlds. So we integrate things from the Center for Astrophysics, exoplanets, computational sciences to try to make discoveries and inferences about planets around other stars. Before I lunge into actually finding other planets, a little bit how they get started. Gas in the galaxy, the mass of the sun, over 100,000 times greater than the mass of the Earth, is swirling around in gas form. Most of it goes into the sun. And less than a fraction of 1% ends up in planets. If you want to study that process of planets forming, you're going to have to track gas making dust grains sticking together to make dust bunnies, becoming little bitty pebbles, pebbles making boulders, all the way to forming planets. And all this happens in a fraction of a percent of the age of the star. So when we look out at the night sky, what do we see? We see a bunch of mature planetary systems. When we're lucky enough to find a young planetary system, it's surrounded by dust and we can't see anything happening. So it's a very challenging problem, many scales, computationally challenging, observationally hidden from view, and makes it a fun challenge to work on. For centuries, all our ideas about planet formation were grounded by our own solar system. And so we made pretty detailed theories about the relationships of why Jupiter is where it is, where Earth is where it is, why there's a gap interior to Mercury. But then we started finding planets around other stars. The first discovery here, our own Penn State professor Alex Wolskins found planets around a pulsar, where no one was trying to look for planets. And subsequently, we discovered planets around sun-like stars, which was recently awarded the Nobel Prize in Physics. And now we've had the rate of planet discovery accelerate, and we now know of thousands of planets around other stars. And this allows us to now look back at our own solar system and put it in context and understand how we're common and how we're special. As we start to get thousands of planets, we start to get greedy. And we say, you know, just finding another planet, not so exciting. What do we want? We want to be able to find and really characterize planets that are potentially habitable, so that we can finally unite the astronomical sciences and biological sciences and look at that atmosphere and see, do we see signs of water and oxygen and methane, and is it in equilibrium? And so being able to look for habitable planets is another area of research that got it started at Penn State. We had Professor Jim Castings coming up with the concept of the habitable zone, the range of distances around a star where a planet could support liquid water. That's critical because, at least on Earth, all life finds liquid water to be critical for at least some stage of its life development. So where there's water is an interesting place to look and ask, is that a place that might have life on it? So we're going to start working towards that. And you might think we'd go out and take pictures of planets. That would be really nice to do. And you're not wrong. We do have a small number of planets you can count on your fingers where we've been able to take a picture of them. But those are the vast majority. They tend to be much more massive than Jupiter, very far from their host stars, certainly not an Earth-like planet with a rocky surface in the habitable zone of its star. And so that's very interesting, but a subject for another talk. We want to use this method, but because it's so hard, it's going to take some really impressive technology. And so NASA, the National Science Foundation, National Academies of Sciences are currently in the process of surveying all of astronomy and astrophysics and asking, what could we do that would be really advancing science going forward? And they're thinking about mission concepts, things that will be likely designed and built in the 2030s, and trying to prioritize between all the competing goals of scientists and astronomers. There are 4 missions currently being explored, and some of them have people working on them at Penn State for different missions. Our own professor, Rebecca Dawson, has been involved in planning the LUVAR mission, shown here. And that mission would be able to look at other stars, find planets around them, and study their atmospheres. But before we actually do that, we need to answer a couple of critical questions. First, it would be really nice if we knew how big to build that telescope. Because in space, size means mass, and lifting mass above Earth's gravitational field is really expensive. And so a bigger telescope, much more expensive, technologically more challenging. We'd love to be able to know what's big enough so that we have great science, what's small enough to make it practical. Another key question would be, where should we look? And when should we look there? Basic questions, and it turns out those are important to be able to make the best use of a large space mission like this. And so what I'm going to tell you about today is how research here at Penn State and with our collaborators across the world is helping to answer those 2 questions to lay the path to a future mission to be able to characterize Earth-like planets. So first, how big of a space telescope do we want to build? Well, you've probably heard of the Hubble Space Telescope, shown in the corner there. And it's a big telescope, 2.4 meter in diameter. I can't stretch my hands that wide. It's big, but by astronomical standards, we want to collect lots of light and have lots of resolution. And resolution means you need a bigger telescope. And so you may have heard about NASA's plans to build and launch the James Webb Space Telescope. That was designed over a decade ago to do cosmology, before exoplanets had blossomed as a field. And it'll do some pretty great cosmology work. It'll be able to add to our understanding of exoplanets. But it's unlikely to be able to study the exoplanet atmospheres for Earth-like planets. And so we're thinking of the next levels of mission, and shown for scale here is the concept of the most ambitious mission. We're sort of currently pricing out this LUVAR large concept of a 16-meter diameter space mission. That'd be quite a feat. And so astronomers are also considering 8-meter options, 6-meter options. Where does it need to fall? And that question of how big a space telescope to build basically translates to how common are the planets you want to study? Maybe Earth-sized planets, maybe potentially Earth-like planets. And recognizing this, NASA launched the Kepler space mission. And its goal was to figure out how common are Earth-sized planets around sun-like stars. And the way it did this was it looked at a patch of the sky that looks like this over and over and over again. Every image you couldn't tell apart. And those images, it's not fuzz in there. If you zoom in, each of those little dots is a star. Millions of stars in its field of view, observed every 30 minutes for nearly 4 years. Why did it take the same picture over and over again? Well, we're hoping that some of those stars host a planet that orbits the star and just happens to pass in front of its star, between us and the star, casting a shadow over the Earth and over the Kepler Space Telescope. And when that shadow is over us, we see a little bit less starlight. So if a Jupiter were to pass in front of the sun, it would block 1% of the starlight. If Earth were to pass in front of the sun for an external observer, it would block 1/100 of 1% of the starlight. Detecting such small changes is hard. The Earth's atmosphere is in the way. The sun keeps rising every day, blocking all the stars. And so we need a mission to get above Earth's atmosphere, away from the sunlight, to be able to stare at hundreds of thousands of stars and look for planets like this passing in front of their star. If it happens again and again and again, we can be confident that it's a planet. We can measure how long it takes to go around its star and measure its size. And so NASA put a lot of effort into this, and years after the mission was over, we had made measurements of the size of frequency of planets as a function of size and orbital separation. And as successful as Kepler was, it actually didn't find Earth-sized planets at 1 AU around a star the mass of the Sun. It found thousands of planets, but not quite that Goldilocks planet that we were looking for. And so it's very challenging to say, well, how common are the planets we want to find? And what can we say from that? And you'll notice that some places here, we have nice little color scale showing you that up in the upper left, planets are quite rare. And as you go to smaller planets, they get more common. As you go further from the star, the frequency of planets is increasing. But then in this bottom corner, where we'd really like to know, we have some gray boxes with upper limits. And those upper limits aren't always as satisfying as actually finding a planet, but they're just as important if you're trying to plan a mission. And figuring out how to accurately place constraints on the frequency of small planets at large separations was one of the projects we did here at Penn State, led by graduate student Danley Su, trying to use advanced statistical methods to remove some of the biases that had affected other methods in arriving at those estimates, and have been now key inputs to this mission planning. So how common are Earth-sized planets? Well, we now know that most stars are actually, there's more planets in the galaxy than there are sun-like stars, and that small planets, presumably rocky, maybe icy, are much more common than planets with large extended gas atmospheres like Jupiter, Saturn, Uranus, and Neptune. And we even have a measurement for the frequency of small planets that orbit closer to their star than the Earth does to the Sun, somewhere between 1/4 and 60% ratio for planets to stars. And that's a valuable number because it tells us that actually Earth-sized planets are common enough. We don't have to look at a lot of stars if we want to find Earth-sized planets to study. Before the study, there were orders of magnitude differences in the estimates for the occurrence rate of planets in the habitable zone. And so it's important to reconcile those and to be able to figure out what is the true uncertainty on these measurements and be able to resolve some of the disparities that have been in the literature. So very proud of Danley for really bringing that to fruition and being able to answer this fundamental question that the Kepler mission was designed to do. As important as that was programmatically to help lay the foundation, I think scientifically, an even more exciting discovery and realization that came from the Kepler mission was that it found thousands of planets where you had multiple planets orbiting and transiting in front of the same host star. And the reason that's so surprising is, if you look at our own solar system, there's nothing interior to Mercury. And so we had rationalized it. We thought, oh, close to Mercury, it's really hot. The dust grains, they wouldn't be able to condense. And we had all these explanations why that should be. But when we looked at nature, we realized actually those planets are much more common than the planets further away. And now by those planetary systems we can see relative to the size of our own solar system, it's actually quite common for stars to have planets bigger than the Earth with large atmospheres, much more dense than our own, that then are orbiting closer to their star than Venus or Mercury are to our own sun. And so this really created a gold mine of opportunities to study. It also created a new problem. All the studies up to then had said, well, let's take all the planets we find, put them in the numerator, take all the stars we look at, put them in the denominator. We divide, okay, we do a lot of work in the middle to deal with the details, but we get out a ratio of how many planets are there per star. And that was one of the things that people asked. But once we started finding stars with multiple planets, we realized there's actually a couple of ways that we could get, say, one planet per star. We could have every star having one planet. It's easy enough. Or we might have a third of stars having 3 planets. And either way, you get 1 star per planet. But if you're trying to design the space mission to go and look at a certain number of stars to study, you care a lot if 2/3 of your stars don't have any of the planets you're looking for. And so now we have to figure out how are you going to account for this when analyzing these systems. And it's also quite important if we want to compare to models of planet formation, because clearly the processes that give one planet to each star are quite different from if you have some stars that are devoid of planets close to them and some stars that have several. So why did we not anticipate that these would be so common. Well, if you look at our own solar system, you might be lucky enough to have Earth pass in front of the sun from your vantage point. About 1 in every 200 places in the sky could do that. You might be lucky enough to have Venus pass in front of the sky, but it's very unlikely that you'd have both Earth and Venus pass in front of the star from one vantage point. And there's no place in the universe you could see Earth, Venus, and Mercury, or Earth, Venus, and Mars pass in front of the sun. So that means we wouldn't recognize our own solar system as a multiple transit system because the orbits, as flat as they are, that's what we tell our school children, the orbits are basically in a plane. Maybe we make an exception for Pluto. No, they're actually not that flat. They're so inclined that it's hard for any one observer to see multiple planets transit their star. Yet when we look at other stars, we see that sometimes the planets are all in a row. And that means you either can see all 3 of them transit or none of them transit. And so now there's a new challenge. When we count those planets and we go, oh, there's lots of stars with a few transiting planets, that could come out one of a couple ways. We could have lots of stars with coplanar orbits and a few planets per star, or we could have planetary systems where the orbits aren't all in a plane, but there's just so many planets, you are able to see 3. And so there's a degeneracy there. And that's always tricky in modeling things. When you have 2 knobs you can turn, and if you turn one this way and one that way, you can make the same observation. Because now we have to figure out, well, how do we balance these 2 things and what's really going on? And so this was a pretty long period project. This is one that took longer than we thought. We wanted to take those systems with multiple transiting planets and extract the information. The most obvious thing, we can just count. How often do we see one planet transiting a star? How often do we see 2 or 3? And so that's one thing we want to be able to match in the observations. We want to look at the orbital periods. How long is each planet's year? And additionally to individual planets, when we have 2 planets on the same star, what are their ratios of their years? So how common are planets that are closely spaced together? How common are they more widely spaced apart? When we look at that, we also see interesting features. Sometimes planets manage to line up in certain orbital configurations where one year is twice the other year, or maybe 1.5 times the other year. And that provides us hints about how those planetary systems formed. We can look at how much light the 2 planets block from their star, and that tells us the ratio of their sizes. And one great thing about that is that even if we're not quite sure how big the star is, so each planet's size individually might have an uncertainty of 10–15%, if they orbit the same star, we can measure the relative size of those 2 planets even more precisely and accurately. We can also ask how long does it take the planet to pass in front of the star. That says how rapidly the planet is moving. And that gives us information about the shape and the orientation of the planet's orbits. And so now we have lots of things we can try to say, can we make a model that's able to explain all of these things? And this took a while. 4 graduate student theses, 2 postdocs, a fair bit of my time, collaborators, other institutions. They moved multiple times during the course of the project. And so now, just last year, we were very happy to be able to publish a model that was able to match all of these observations. In developing that model, though, we ran into a problem. The full model was pretty complicated. We had lots of knobs and parameters to turn. Each evaluation took a fair bit of time. Now, you may say a few seconds, who really cares? But if you have 100,000 stars in the field of view, you need to generate 100,000 planetary systems around every star. And then you say, well, I want to understand, when I see something kind of funny, is it just luck, or is it actually statistically meaningful? So you want to generate not just one simulated universe, but hundreds of simulated universes to establish which of those patterns are significant and which could just be chance. And then you want to say, well, which of these features are important, and how does it change if I change the frequency of planets, or the degree of coplanarity between their orbits, or how circular, elongated their orbits are? And so each of those knobs you have to turn back and forth, turn this one up, that one down, trying to compensate for the thing. And it takes a lot of evaluations of these models. So to make that practical, after making this model to model the planetary systems, we then needed something else that was just a whole lot faster and basically gets the same answer. And so that's an example where you hear about machine learning, allowing us to find a mathematical model that's faster than our more detailed model, And by being orders of magnitude faster, we can now evaluate millions of times to perform statistical inference, trying to come up to which conclusions are robust, which conclusions might just be chance. The way we do that is we generate all these catalogs, and for each of those catalogs, we compare the number of planets, the periods of the planets, the sizes of the planets, how long they pass in front of their star, their period ratio, all these properties, and we go through those catalogs and ask which ones are consistent with the data, which ones are not. We put all the ones in the good category, and we say, what's in common about these models? What properties are actually important to being able to reproduce the observations of extrasolar planets from NASA's Kepler mission, and which ones are there multiple ways we can try to turn them and they don't affect the results. So Matthias, he is a graduate student in the late stages of a dissertation who led this project and has now not just generated catalogs for these comparisons, but also the code so that other researchers can build on these. And just last week, we were looking at the first paper to come out, looking at our model and trying to find some new little wrinkle in which, oh, wait, we found something that doesn't quite match. And you can kind of be negative, oh, no, there's something that's not quite right. Or you can say, aha, a new piece of information we can incorporate. And so that's how the scientific process works. Someone coming up with a model that does better than anything before, someone else identifying a way in which it could be even better, and iterating through that process. And so we have just a great opportunity through our collaborators and colleagues who have contributed to the Kepler mission, helping us make these even better. One of the big questions in planet formation that this allows us to address is, to what extent do two planets that form around a star know anything about each other? Are they basically planets being flung around? And the space between planets is humongous. And so you might think that one forms over here, one forms over there. They don't know which mass their neighbor is going to be. Or it might be that when you have one star, the same disk that forms them, there's some things that they have in common. Maybe they form in a similar location, have similar sizes or masses. And so one of the key questions that we explored in this study was comparing these two models, and we found that indeed, planetary systems have planets that know about each other's separation, size, and mass. We're able to quantify that. And that's very valuable because then we get to compare it to simulations. And so other researchers in our group, please play, construct these planet formation simulations that are much more detailed, and track the formation as small planets merge and grow, interact with the disk, they can migrate in, and then we get to compare the final locations of the planets, final size of the planets in these simulations to reality. And so this work has led to a new view of planetary systems, largely thanks to NASA's Kepler mission and the ensuing analysis. And we now recognize that most stars have a planetary system. We now know that planet formation produces planets that are clustered in their masses and sizes, and that's a strong constraint on these planet formation models. The planets, the indications of residence in their orbits. And perhaps most interesting, we now know our solar system is not typical. We can identify multiple ways in which our solar system is in the minority. Our solar system is devoid of planets interior to the orbit of Mercury. There aren't any planets that are between the Earth with its sort of infinitesimally thin atmosphere, very thin, you can look up and see stars through it, to the dense atmospheres of Uranus and Neptune, Jupiter and Saturn, where you can't even see to the surface. And also further out, other surveys using other methods I'll talk about next have shown that Jupiter analogs are also in the minority of star systems. And so collectively, we're not saying that the solar system is rare, not saying it's less than 1%, but it's not in the majority. And that means there's a lot more out there to explore and to learn about. And so then we come back to the question of how big of a telescope do we build? Do we say most stars have planets, so we can just look at the nearest stars and we'll learn about some planets? Or do we go big and say if we want to find planetary systems like our own, we don't just want to find summer-sized planets, some of them in the habitable zone, but enough to be able to match all these exciting properties of planetary systems that we've been discovering with Kepler. There's another question I used to motivate this talk, and that was, when should we look where? The missions that are currently being contemplated are being designed to be self-sufficient. So early in their mission lifetime, they would go out and they'd look at maybe 100, 200 stars. And for each of those stars, look once, do I see anything? If not, go, remember that one? We might want to come back to it later. Oh, let's wait till the planets have gone around some of their orbit. Hey, still any planets now? No, okay, go look at some other stars. Come back maybe a third, fourth time to make sure that they just didn't look when the planet was too close to the star to be recognized. And as a result, there's sort of an early phase of the mission where you're searching, and then near the end of the mission, they could be trying to study the planets they found. But what if we could bypass that first step? What if we could find planets and understand their orbits before the mission's launched so they know which stars to look at and when to look at them? Well, now we accomplish a lot more science with the same telescope. Maybe we build a smaller telescope. Maybe we study more planets. So how are we going to do that? We're going to use a different method. Instead of looking at stars and picking only the ones that happen to have orbits aligned so that their planets pass in front of their star, we want to find the nearest planets. So we need a method that's able to study those. And there's another planet detection technique known as the Doppler or radial velocity method, where we take the starlight, split it into a spectrum, look at minute variations in color to be able to search for planets around nearby stars. But the physics behind this is you have a star and a planet, they're orbiting each other, and as the planet goes around the star, the planet also wobbles about the center of mass, and that motion causes a Doppler effect. So that's when you're sitting on a street and you hear an ambulance going, meow. Right? You're hearing that frequency of sound change. As it's coming towards you, it's high. As it goes away from you, it's low. Light does the same thing, but instead of being the speed of sound that sets it, it's the speed of light. And since that's so much faster, our eye never notices, but our instruments do. And so Penn State is now leading two very important planet surveys, led out of the Hobby-Eberly telescope in West Texas, 10-meter gigantic telescope, and also a smaller telescope in the Arizona desert. These two surveys, why two of them? They're highly complementary. They study different types of stars. The telescope there, Penn State built an infrared instrument that's able to study low-mass stars that emit most of their light in the infrared. And for the second one, it has a slightly different instrument that's designed to study optical light coming from stars more like the sun. So now it's empty, but not that long ago, if you'd been at Innovation Park near the Penn Stater, you could have walked by the lab where Sir Brett Mahadevan and his team were building these instruments. And they're really remarkable pieces of technology because inside those instruments, they're controlling the temperature and pressures to a remarkable degree. You know, millikelvin, microkelvin, just teeny differences will cause the instrument to expand and contract. Small amounts of pressure can cause light to bend, and so they have extremely stabilized environments inside those instruments. And so those two instruments funded by NSF, the National Science Foundation, and NASA were able to put Penn State in a position where we now can be leading these planet searches. Last year, the Habitable Zone Planet Finder began its science at the Hobby-Eberly telescope, and the data that comes off the telescope looks something like this. You see two little lines, a solid line and a dotted line. The solid line isn't actually solid, it's the starlight. And each of those little wiggles reflect where there's an atom in the upper layer of the star cooler than the gas below. And as the heat generated by the nuclear fusion at the center of the star emerges upwards, the cool gas absorbs light at certain wavelengths. And we can measure those in a lab. And those are constants of nature. And all we need to do is recognize that line shifts a little bit. The problem is, in our lab, we have pieces of technology. And so those stabilizing the instrument's temperature and pressure is critical to be able to have a constant environment. Even then, it's not perfect. And so the dotted line below is a calibration source, something that's designed to be able to measure the shift of the star spectrum relative to the stable, either a laser frequency comb or some other technology developed at Penn State to be able to precisely calibrate the shifts in the starlight as the star moves. It got some of its first data last year, some of the most precise data yet for measuring the velocity of a cool star, and is in the early stages of beginning this planet survey. And so this is what I mentioned at the beginning. We're in the beginning. We don't really have results yet, but we're really excited to be in the process of surveying these stars and looking for low-mass planets around cool stars. The second instrument works kind of similar. Another image of the detector. This is its first light image from released in January, where it looked at the star 51 Pegasi b, and you have those solid lines are actually the starlight, and the dotted lines are actually the calibration source, and we compare how those two lines move relative to each other to measure the Doppler shifts. And these are really small. So an Earth-sized planet would cause a shift of, I think just a few thousandths of a pixel, and that corresponds to less than 10 silicon atoms motion on that detector. That's why they have to be able to measure this extremely precisely. The good part is they succeeded. The bad part is there are new challenges. We used to treat the sun as if it were some perfect idealized light source. And what we measured when it moved was the Doppler shift of the star. But it turns out the star is not a billiard ball. It's actually a big ball of gas. There are star spots that are dark and rotate across the star. There's the surface of the star isn't a solid surface, but rather is a bubbling layer of hot gas clouds rising, cooling off, and falling back down. And so we recently had the new National Solar Observatory take some of the most impressive high-resolution data yet, where you can see sort of the bubbling of these granules of hot gas rising and falling. And those things mean that in addition to seeing the motion of the star due to the planets, we're also seeing changes in the spectrum due to the surface of the star. And so we have a team of graduate students and postdocs working on developing new methods to be able to measure small Doppler shifts due to planets in the presence of these forms of stellar variability. So how does that work? Here, greatly exaggerated shifts of the spectra are occurring via the magic of PowerPoint. But if you zoom in on any of these regions, you see that actually those little dark spots are these absorption lines. And some of those lines just shift back and forth due to a planet. But other times their shape changes due to, say, a spot rotating across the star, causing the shape to change. And that shape change can be mistaken for a shift of the line. And so we're trying to find ways to be able to recognize and distinguish those two differences. We do that with various forms of machine learning or artificial intelligence, data sciences. We're trying to recognize which changes are due to the star's actual motion and which are due to stellar astrophysics. And all this gets fairly complicated. And after you're kind of proud of, oh, this thing's working really well, you're happy with what it's doing, then you go to tell someone else, oh, look how great we did. And they say, that's kind of complicated. I don't get it. How do you know it works? And you're like, well, I thought really hard about it, right? But then it's like, well, how do you know what's going on? So we need ways that we can validate these models. And this has direct analogs in our day-to-day life. When you hear about algorithms, whether they're being designed to drive your car or sell you something on the internet, how do you know when they're working the way you want and when they're doing something that you don't want? Well, one advantage of science is there really is either a planet or not a planet. It really does have a mass and an orbital period. There's a true answer. It's not just sort of what widgets people are buying this week. And so we can try to use science as a way to test these algorithms and learn about when we can trust machine learning and when we shouldn't. One way we do that validation is through simulated data sets. We have models to be able to simulate the evolution. We have the spectrum of the star, and then we generate other ones. We turn knobs, and then we study how the spectrum changes in different ways. And we can do that to study the effect of star spots on one hand. Then we can, on the other hand, study the effects of that boiling surface of gas rising and cooling, how it changes the shapes of the lines there. And we can generate data sets that we can then analyze where we, or at least one person on the team, knows how they were generated. And another member of the team can try to analyze them and figure out what happened. And then after a while, you check and see if you got it right. Now, all this gets fairly expensive in terms of computing power, because now we're simulating the sun spectrum over and over again. We're simulating planet surveys. We're analyzing that data with very different approaches, and we're trying to recognize which ones work, how well. And so to do that, we make use of the Institute for Computational and Data Sciences. New name there is designed to trick speakers. They run Penn State's Advanced Cyber Infrastructure Project. So there's tens of thousands of CPU cores, petabytes of storage, providing the entire university with the facilities they need to be able to perform these types of inferences. And so we've made extensive use of that, not just the physical infrastructure, but also the engineers who keep the thing running, the domain experts who can assist us with making codes run efficiently. And it's quite a sight, data center. It's really hot. It's a pretty cool place. But now they've made it secure, so you can't visit it. Sorry. So that's one way we validate our models, is by simulations where you can test things. But simulations are never perfect, right? And so how do we know that when we take it from our simulated universe and we get the right answer, it'll work on the real universe? Wouldn't it be nice if there was a star where we knew all the planets in it and we could model it just exactly? Well, our nearest star, we do. And so here's a picture of a solar feed to be able to study the sun. This dome is where the 3.5-meter wind telescope is, the one that's feeding that new spectrograph. And on the roof is a small little device that takes sunlight, sends it down a fiber optic tube, and sends it to that spectrograph. So during the daytime, when they're not studying stars, they can study the sun. We can observe this hundreds of times every day, well, at least it's not cloudy, and learn a lot about our sun. And that gives us a chance to both test our instrument. And so this actually allowed us to demonstrate to NASA that the instrument was working as well as we said it would before it got shipped. And then also allows us the ability to observe the sun and ask questions about whether or not it would be able to recognize the algorithms we use, how they would fare on the sun. And so now we have real data for one star, not for all stars. All stars aren't the same. And so we sort of have to balance these two things. In our computers, we can simulate other stars and see how the differences between stars affect our ability to recognize planets. And then we can test on a real star with very high signal to noise, lots of observations. And together, that's how we're going to try to validate these models. But it's a work in progress. And I think it illustrates nicely the cycle that modern science goes through. First, we have some basic physics, planets orbiting stars. And we say, well, we want to observe those. We'll need some telescope time. We need some instruments at the back end of the telescope to collect the data and sort the light by its color, to have stable calibration sources to compare it to. But then once we reduce that data, then we go into advanced statistical modeling tools. And then that tells us in turn about the physics. It used to be we learned about the planets. Now we're learning about the stars and the planets. And then as we learn more of the stars and planets, that then informs how we conduct our next generation of planet surveys. And so this cycle is not a straight line, but rather a feedback loop, as each of the different researchers at Penn State from different areas collaborate with each other to try to make something better than any one of us could do alone. So coming back to the two critical questions I identified at the beginning, we had how large a space telescope do we build and where do we point when? So I've told you about how we've been able to provide the information necessary to plan accordingly the size of the next generation spacecraft to characterize extrasolar planets. And then some of the work going on at Penn State to be able to find those planets before these missions launch, characterize their masses, and tell them when they should look and where they should look at it. And one thing I didn't dwell on in the beginning, but when you look at a star, it's really bright, and its planets are quite small and faint, and they're lost in the glare. So if any of you were lucky enough to see the solar eclipse not recently, you may have got a chance to see not the bright sun in the center, but the corona. Something you never see you see on the internet, but you never see it in person except during a total solar eclipse. And so in the same way, these missions, they're going to go look for small planets and other stars, need a way to block out all the starlight and to look out in the little wings to see, are there any faint fuzzy dots that could be planets we could go study? And so if we knew when and where to look, it would allow us to use a different type of mission. So one of the concepts being explored is a star shade. So instead of having one telescope that just points somewhere, you actually have two spacecraft. One's your telescope, and one is a gigantic, I think this is like 50 meters in diameter, it's enormous. And it's to fly far away and position itself precisely between the telescope and the star you're looking at. And then you want to look at a different star, and so this thing has to fly around the solar system to get it between the spacecraft and the next star you want to look at. And this is actually really good for blocking out starlight and studying the planets around that star. The problem is, it takes a long time to move your spacecraft from one star to the next. It's no longer just sort of like, right, so now you're talking days to be able to move things, position them precisely. And so that's why not just knowing which stars we want to look at, but when their planets will be widely separated from their stars and be at a distance that the telescope will see them, would allow some, I guess I'd say, alternative, innovative designs for missions might become practical if we can be able to find these planets before the missions launch and give us planets to study. Once they are able to separate the light from the star and the planet, then we can look at the different planets and take the spectra not of the star, but the spectra of the planet. And if we do that in the solar system, we'd have some planets that look basically like a rock. You'd have other planets, moons. Some of them look icy. Some of the planets have a thick gaseous atmosphere. And depending on the planet, different types of atoms and molecules in their atmosphere that can be recognized with optical and infrared spectroscopy. So that's one of the types of observations we hope to do with this next generation of spacecraft. The other thing you can do is you can sit and watch that planet, and you'll need to observe a long time to be able to build up the signal to noise to recognize atmospheric features. And as you're watching, if that planet's rotating, oceans and continents will come into view and rotate out of view. And so now you have, as a time series of data, a measurement of the brightness of that planet as a function of time, changing due to what features are being illuminated and in view from your observatory. And so in addition to studying the atmosphere through spectroscopy, we'll be able to study the surfaces of these planets by looking at the temporal variability of the light they reflect. And so these are some of the things that we hope to be able to do in the 2030s if NASA and NSF decide to go forward with some of the missions being proposed. But there's actually a lot of interesting astrophysics. People are also interested in far infrared observatories of other galaxies. X-ray astronomy is having lots of exciting new developments thanks to instrumentation and detectors being developed at Penn State. And so there's other missions being considered. And we might have to wait till the 2040s or 50s. So it's lots of exciting things, an embarrassment of riches, but also lots of exciting opportunities for the students to pursue throughout their careers as scientists. Before I wrap up, I want to say a few things about how all this fits into Penn State's mission. So we've talked about a lot of searching for planets, curiosity-driven science. We're interested because it's just interesting as humans to find out what's out there, to see how the Earth and the sun and our solar system fit into our galactic context. But it turns out that the process of studying these planets, it relies on some large data sets, some advanced statistical methods, high-performance computing. Those three things are basically the building blocks for AI and machine learning. Our students learn how to analyze images, things like self-driving cars, medical imaging to recognize features in MRIs and X-ray images. And so these skills they develop in the context of astronomy can be translated to lots of other fields. And indeed, many of our students go into astronomy, but many of them go to industry, to areas that we didn't originally anticipate, but find use for the skills they develop. Now, why is it that astronomy is particularly good at that? Well, stars don't care about their privacy. You don't have to worry about the value of the data that Google's collected on you. All the data we collect in astronomy, we're willing to share. We say, sure, let's let the students play around with it. And so recently I had an interesting experience. Penn State has a new data sciences major, and it's their capstone project. They need to work with someone on a real problem where there's no known answer in advance. So I worked with 3 teams of science undergraduates from this data sciences major and gave them some projects related to NASA's Kepler mission and trying to understand which of the objects it found were planets and which were not. And it was interesting for them because it gave them a real-life data set. They got to tinker around with it. Interesting for me because I got to see what are the students who are not trained 2 decades ago, but learning about the machine learning algorithms from computer scientists today and see how they approach these same data sets. Some of the things they did were kind of silly as an astronomer, but some of them were things I hadn't thought of and actually suggested some pretty good ideas. Right? And so that interaction of scientists, statisticians, computer science is exactly what we're trying to do with things like our data sciences major. And this curiosity-driven science where we're willing to share data and methods and build on each other is a great way to help educate students. And with that, I'll take questions.
All right, thank you so much, Dr. Ford. I know people are going to have a lot of questions to ask, and so if our 2 Science Lion Pride students could come around, please hold your index card high so they can see it, because they have to run around all these up and down the aisles to make sure they collect everybody's. But while they're collecting people's questions, I'd like to pose one to you first, just to get us started. You talked about the observatories and telescopes that might be built 30, 40 years from now, but are there any current space missions or near-term space missions that might help us in the search for exoplanets?
Yeah, that's a great point, is that well, we as scientists often have to focus on 1 or 2 projects at a time. As a scientific community, there's lots of things happening all at once, and they all support each other. So right now, NASA has the TESS mission, Transiting Exoplanet Survey Satellite. And it's a successor to the Kepler mission. Kepler stared at one patch of sky for 4 years to learn about the planets in that field of view. But the closest planets, the planets around brighter stars, are likely in other parts of the sky. And so this mission is scanning the entire sky so as to find more nearby planets that will be more amenable to study with methods like the Doppler method that I described in the second half of my talk. There's also other missions. I mentioned the James Webb Space Telescope will be used to study these transiting planets when they pass in front of their star. It'll block some of the starlight, and we can probe the upper layers of the planet's atmosphere. Not the deep layers, probably, but learn about what are the gases high in their atmospheres. We have another mission that's still in the stages of being built. They're cutting metal at this point, W-FIRST mission. It's primarily a cosmology mission, but it's planning to fly the first sort of space coronagraph testbed. So a high contrast coronagraph testing the technology required for the missions I showed today. And so those missions will give us information not just about the direct imaging, but also is going to look for the gravitational microlensing effect. So if you heard Chad Hanna's talk, was it last week or 2 weeks ago, where he was talking about gravitational waves, there we can actually detect the gravitational perturbations of planets as they pass in front of distant stars, and allow us to learn about planets that are far from stars or around very cool stars that we don't detect via these methods. And together, piece those together to get a census of planets that both close to their star and far away. And so we actually are in a great time where we have several missions ongoing and in the works to be able to give us a broad picture of what planetary systems are like at many scales.
All right, thank you. It'll be very interesting to see what comes out of all those missions as they happen. We have one audience member who wants to dig into spectroscopy a little more. So as you analyze by spectroscopy exoplanets to find elements and compounds, are the results of the spectroscopy affected by the color or spectrum of the star, or are all the stars with possible Earth-like planets, do they have similar spectra?
Good question. So when we look at stars, sometimes we focus on ones that are more similar to the sun, but even from stars that are, say, 500 degrees hotter or colder, I mean, 500 sounds like a lot to us, but compared to the temperature of the sun, it's kind of small. There are stars much, thousands of degrees hotter or colder. There are differences, particularly in which of those lines are excited and effective at absorbing light and which ones are not. And so there are differences from star to star, and there may also be differences because the planets that form around a star may be influenced by what was the composition of the material in that gas cloud. And so one thing astronomers do now is they try to study the composition of the star that they see, and they we'd really like someday to be able to compare those compositions. Right now we compare it to just the frequency and the size or mass of the planets we find, but someday we may be able to compare the composition of the star to the composition of the planet. Now the light we see, we can see it in a few ways. Sometimes if we're looking in the infrared, we're seeing light that's generated deep in the interior of the planet and goes out through the atmosphere, and the features we see are the absorption of the planet's atmosphere of the infrared light being emitted. So then the star's input isn't so important, but the things I described today, we'd be seeing the reflection of starlight. So the starlight comes and hits the atmosphere or surface of the planet, bounces off towards us, and that means that it's, to first order, it's just a reflection of starlight. And then we have to be able to, fortunately the star is much brighter, so it's really easy to measure the star compared to the planet. So if we can measure the planet spectrum, we'll have a really good spectrum of that star. And then compare those two to see where do we see the ratio deviates, and there's places where the star the planet is absorbing more light than just the reflection of the starlight. And so that's how we'll be able to recognize atmospheric biomarkers or surface features in the spectrum of planets.
Okay, thank you. We have another technical question digging into one of the methods. Somebody was curious when you were talking about determining continents and other features. How can a telescope determine what is a continent versus what's an ocean on a distant planet?
When you look at the ocean, you probably think it's blue or something. But if you actually look at how bright it is compared to something like sand or forest is actually pretty dark too, but the ocean is actually, most of the light goes into the ocean, right? And it bounces around, and so it doesn't reflect very much light. And when it does, it reflects it in one direction. So if you ever sort of maybe been looking, you see like the reflection of the sun, and it's really bright, and you kind of turn away, you're basically seeing a mirror. The ocean is a nearly flat surface, and there's a small portion of the ocean that's reflecting the sunlight right at you. But if you look just a few degrees away, now it's perfectly dark. And so the ocean is a highly directional reflector. On the other hand, continents, land, when you look at it from this angle or that angle, you don't really notice that the brightness of the rug changes depending on whether you're looking at it from an angle or straight down. It's reflecting its light much more uniformly in all directions. And so since we're looking for one direction and we're looking at a planet that has, there's one place on the planet that would be really good acting as a mirror reflecting that starlight towards us, if there's an ocean there, we see that reflection, and if there's not, we don't. But the rest of the planet surface that's illuminated in view can contribute other light that's not in sort of the mirror configuration for us to see it. And so as things rotate into and out of that special location where the ocean can act as a mirror, allows us to recognize when it's being covered by land or oceans. Of course, it's complicated because oceans might have clouds over them, rain to make the water, and clouds also are very diffuse, but they're also very bright, much brighter than the ocean. And so again, it will be the type of problem that's very complicated to analyze. And so for the moment, most of our simulations have focused on understanding how do things like cloud cover and oceans of continent affect the light we see, and we have yet to solve the problem of how we take what we see and we figure out what's there. So there's an inverse problem where we have to kind of do the opposite and figure it out, and those are always harder. So hopefully we have hopefully we have as little time as possible to figure that out, but I have a feeling it'll be at least a couple of decades before we have to solve that problem.
Well, it's good to know, something for us to stay tuned on 50 years from now, maybe. So we're going to move from those kind of technical methodological questions to something a little broader. So one of our audience members wanted to challenge you and ask how what you've talked about today in the general field of astronomy might have a connection to the overall theme of this talk series, which is predicting the future, because I know a lot of the astronomical data isn't necessarily from or related to the future. So they wanted to know a little bit about that, if there is any connection, and whether any models or findings that come from this kind of research could potentially enhance other scientific efforts to do that kind of more future prediction type modeling.
Sure. So the way I sort of made the connection to predicting the future was in, we had this goal of building a future spacecraft that will be able to study and characterize Earth-like planets. But figuring out what to build is the challenge. And so we're going to use the observations we have in hand and the observations we hope to conduct over the next several years to be able to understand what the planets in our galaxy are like, to predict the distribution of planets, to understand where planets will be when, and those predictions can then be very valuable for deciding how big of a telescope to build, which stars to look at, and when to look at them. And so that was sort of the way I structured the talk to address that predicting the future observations we hope to do with these new telescopes to characterize potentially Earth-like planets. Perhaps another way you could think about it is in terms of when we have one planetary system, we can see how it is right now. But that's actually a snapshot in time. And if we want to understand how it formed, or maybe how it will evolve in the future, we need to understand the orbits of those planets very precisely. So another thing that my research group and others here at Penn State work on is trying to very precisely characterize the orbits of the planets today and recognize clues from those that tell us about either how they formed in the past or how they'll evolve in the future. So for example, our sun, it will eventually, billions of years, start to lose mass and expand. And as it does so, the orbits of the planets will spiral outwards. The closest planets, Mercury and Venus, will fall into the sun because the sun will expand more rapidly than their orbits expand. Mars will expand fast enough that it managed to escape, and people debate whether Earth will fall in or be able to survive. we have a few billion years to solve that problem. And so that's an example of how planetary systems evolve with time. And then we want to be able to ask not just how does our solar system evolve with time, but how these other planetary systems that are very different in some important ways, how do they evolve with time? And so we also study the orbital evolution, both in the past and in the future, of these planetary systems, either rewinding or fast-forwarding the clock to gain insights into the processes of planet formation.
Okay, thank you so much. I'm going to attempt to combine two related questions here because they're both about our fundamental definition of life, which is important to the search. So in terms of life in the solar system, because you mentioned that the solar system is kind of atypical, and so is it possible that there is life that doesn't need water and oxygen and things how we as we're used to seeing life here? And if it is unique, would it make sense to try to find solar systems that are more similar to our solar system if we're using this water and oxygen, kind of what we know as life, as our definition for life?
Yeah, there are different approaches to what I would say are philosophical questions. And so, for example, one strategy to look for life beyond the Earth might be to just go about your everyday life and wait if someday you become abducted by aliens. Right? You might. I can't say it's impossible. But if you don't, you haven't really learned anything. On the other hand, if we are able to say, here are stars that are similar to the sun, and here are planets whose composition and temperature are similar to the Earth, if you look at 100 of those and you say, in all of those, I only saw highly reducing atmospheres with lots of hydrogen or highly oxidizing atmospheres with lots of oxygen, they were never some of both mixed together, that would be pretty compelling evidence that the lucky balance of life's conditions to get started happens rarely, around 1% or less on these types of planets. And so when we design a science experiment, we don't just want to do something that might have an interesting result. We want to design an experiment that if we don't find something, it also has an important result. And so when we say things like, let's figure out what's a habitable zone, we don't really know what the habitable zone is. It's really a terminology and a structure for structuring the way you conduct a search. And the way you do science is you say, here's something to be interesting either way, whether I find something or I don't. And so it's possible that there's life that doesn't use water, possible life that doesn't use carbon. And so we can't rule those out. But what we can do is we can say, let's go looking for what we think is plausible based on what we know about life on Earth. And if you think back to the Kepler mission, we went to go look for how common are Earths, and we found out actually there are a whole bunch of super-Earths orbiting closer than Mercury. And so in this process of saying, here's how we're going to design our mission around looking for Earth analogs, in the process, who knows what we'll find? We might find that there's evidence of out-of-equilibrium chemistry on planets that are way hotter than we thought were possible. And then we have to ask what elements and molecules could support out-of-equilibrium chemistry, perhaps life in that environment. Or we might find it when places that are much colder. And then we have to ask, is it actually that cold, or could there be some geophysical processes like geysers and outgassing on those planets that's allowing them to stay warmer than we might naively think based on their distance from their stars? And so we have to keep in our mind both that we have limited knowledge about how life got started on Earth, so we need to be open-minded, but also structure our investigation so that we learn something regardless of the outcome of the search. And that's what we're trying to do with these concepts.
So does that balance between needing to start somewhere and then using what you find to figure out where you go next?
Yep.
And so they're kind of diving into a slightly more technical question again, but you discussed the process for how you're studying variation in the surface of the star using the instrument on the roof of that observatory. Could you use other nearby stars like Proxima Centauri, and use similar methods to to explore similar questions?
Yes. So over the past few months, I've been involved in a group of scientists sort of commissioned by NASA and NSF to try to figure out a plan for reaching these goals. And so this is exactly one of the things we were thinking about is how do we balance the fact that the sun is just one star, and we need to make sure that what we do works not just for clones of the sun but other stars, with the fact that the sun is a whole lot brighter than any other star. And so if you need to collect enough light to analyze that star, you need a much, much bigger telescope to be able to do that, even for the nearest stars. And so there's talk about things like we might get the NUID instrument and the HPF instrument, and some of our collaborators, the Express instrument led at Yale and the Espresso instrument led by people in Geneva, and try to get all of us to agree on, I don't know, 2 4, maybe 6 stars and say, can we all look at a few stars and piece together through all these observatories together enough observations that we can do something that's better than we do for our search of planets around 100 stars. It still won't be as good as what we can do with the sun, but as a stepping stone and a bridge that we'd be able to carry out a similar experiment validating our methods on stars that are favorable for these studies, even if not nearly as bright as the sun.
All right, thank you. I just want to remind everybody, I still have a few questions down here, but as things pop into your mind, feel free to jot it down and wave them. Our students are ready in the back to grab your index cards from you if you think of anything while he's answering some of our other questions. I'm going to pose a very future-related question that we probably won't know the answer to for a long time, but it's from William, who is one of our audience members who's 10 years old, and he wants to know what you think about the probability of him living on a different planet in his lifetime.
Well, planets are far away, and stars are even further. So technologically, I mean, people actually are conceiving of maybe we could send a very small spaceship. They call them things like nano spaceships because they're basically just a little microchip to another star. It would be a big effort, and then you kind of wonder, is it worth the cost to send one microchip to another star? You find out that once you get there, you're going so fast that you whiz by really quickly. If you actually wanted to be able to stop once you got there, how are you going to do that? Where's your power? Oh no, it's no longer a microchip. So it's very challenging to imagine interstellar travel being able to reach, let alone sort of stop at another planetary system. So when we think about studying other planets, we're normally thinking of via remote sensing. So we're not doing in situ measurements, like if you go to look for life in a nearby stream or pond, right? You can take a little sample, you can put it in a microscope, and you can study it directly. You can intervene and conduct an experiment. In astronomy, we're normally an observational science, so we don't have the ability to actually experiment on planetary systems, to set up 10 petri dishes and see if they all come out the same. We observe remotely, and that's a different style of science, and so there is a challenge of how you do that. Personally, I'm not optimistic that people will be traveling to other stars in our lifetimes, but that doesn't mean that people shouldn't be thinking about the possibilities and dreaming big.
All right, so William has plenty of time to see if he can help get us there, for sure. These next two questions, they're not completely related, but they're about like small details that appeared that people were curious about. So sure. I'm going to pair them, and you can answer them in any order that you'd like.
Maybe I'll forget if you pair them. So unless they're really similar,
do one at a time.
I'm always afraid I've only answered half of someone's question. So.
On some of your sun-related slides, there was an outline of Texas that appeared somewhere on the slide. So they were wondering what that was.
I think that was probably just for a size comparison. Maybe I should have. There he goes. So this is from the National Solar Observatory. Recently got a major upgrade. There's a new telescope on Mount Haleakala in Hawaii. And so they're very proud of this animation. Oh, I might be able to jump to a zoom in of this. Let's see if I can do that. And so there's sort of a zoom in of these bubbling sort of gas cells that rise and fall. But when you look at this, I saw someone say it looks like caramel corn. But that's a different scale than the sun, and so the purpose of that little illustration was to help you get a context for the size. And I guess Texas was a big state that people have heard of, so I think that's why they put it there.
It's almost like one of those little caramel corn sizes would be Texas.
Yeah, so it's helping you appreciate how big these are. They're enormous, and yet they're a small fraction of the surface of the sun. At any time, there's tens of thousands of these cells rising and falling in different places. So it's fascinating observations, and these new observations are the types of things that inform the simulations we do to try to be able to figure out how to analyze data that has this very messy surface in the star happening continuously.
Okay, well that was great to know, and I had noticed Texas, but I'm glad that they asked that question because it's really interesting to know. And the other question that I'm glad somebody asked, because I was also curious about this, is on the sunshade movie that you were showing. What is the purpose of the petals at the side? Because you'd assume, I guess, that it would just be a circular way to block out the middle. But is there a purpose or a design reason that those exist?
Yep. So this is, let's see. I know of some people here who might be familiar with optics, but others who probably haven't taken their optics class yet. So I'm trying to think of how to phrase this one. If you have a circular spot and you cover it up with a circle, you get a pattern of circles. You can think of it, even if you don't understand the details of physics, by symmetry, there's no reason that, say, north and east can have a different pattern, right? So you get rings around that spot where the quantum physics of light's nature means that you don't perfectly block it out, but there's light that leaks around the edges, and it leaves these rings. And so that's problematic because we want to look for planets, and the rings can be brighter than planets. So the ratio of the brightness of the Earth to the sun in reflected light is about 10 billion. And so if 1/10,000,000th of the starlight seeps out around the edges, it dwarfs the poor little planet. And so what we want to do is to say, well, we want to have a design that allows us to have some angles where we block the starlight really well, and others where there's sort of a wedge or a gap where actually the light's being thrown into that direction so it doesn't go in some other place. And then we create these little windows, notches in our pattern, where we can look for planets. So it's not just which star are you looking at, it's which orientation are you putting the shade at. Because you have this little wedge of opportunity where if there's a planet right here at this distance, left and right, not too close, not too far, that's where you could detect it. And so a lot of work has gone into engineering both the optics of what's your ideal design, but then also how do you get this thing up there, right? So we can't launch something that's 50 meters in diameter into space. We have to fit into a rocket and have it unfurl. And so then there's a little bit of the technology of how do you make a self-unfolding mechanism that maintains a perfect shape, and you need. So there's a combination of optics and mechanical engineering to be able to make a shape that would work both technologically from the engineering aspects and then the optics point.
Okay, thank you for that clarification. For the Doppler experiments that you were talking about, is the support for that? You've mentioned, obviously NASA is a big supporter and funder of this kind of work. Are there any other sources of support and interest in this kind of work? And what is the landscape of who's interested in doing these kinds of experiments or designing these kinds of instruments?
Yeah, so the work here at Penn State has support from obviously Penn State itself, also NASA, the National Science Foundation, also the Heising-Simons Foundation has supported, for example, the little solar add-on to be able to observe the sun. And so there's different sources of support locally, but also it's a really international endeavor, right? So there's a common interest in finding planets, and so we have colleagues at other institutions and other countries, and so there's agencies in Canada and England and France and Germany and Switzerland and Japan, and I don't know all their acronyms, and so there's lots of different organizations that often contribute, say, maybe a subsystem to a project or one experiment, and then by collaborating and comparing our notes, we're able to do more than we would be able to if we only could work from one country or organization's resources.
Okay, thank you. Our next question comes from a student at Penn State who wants to know how they can prepare themselves to integrate themselves into the study of exoplanets and similar research. Potential recruit for your lab, potentially.
Excellent. So exoplanets is a broad field. So as I kind of highlighted here, we have some folks who are building an instrument. So they're optical engineers, electronic engineers, mechanical engineers, thermal stability, like all sorts of engineering aspects. We also have some people who run surveys. So they take that instrument that was built over in Surabhat Mahadan's lab, and they did figure out how do we know which star to look at for how long, when, and conduct that survey well. And then we have other folks who take the observations that were conducted and analyze them to try to find which planets are there and what are their properties. And then someone else goes on and tries to understand the processes of planet formation from them. So there's a variety of different fields, and depending on whether you want to be involved in building, more of sort of an engineering background, or conducting astronomy, more of an astronomy background, or maybe some of the theoretical aspects, the computer modeling, computer science, statistics, data science programs, each of those can have a path to contributing to the search for exoplanets. Also in planetary sciences, so Penn State, we have a College of Earth and Mineral Sciences, and there's kind of a little bit of we have faculty from both colleges working on planetary science things. There is a planetary science major actually run through the astronomy department for people who are interested in mostly sort of the planets our own solar system traditionally, but now we're needing to integrate the lessons we learned when we can do much more precise measurements of, say, Mars or asteroid in the asteroid belt, or Jupiter, Saturn, the moons, to compare them to, say, planets or other stars. I think all of those probably have a few things in common. So almost all of them will have a fair bit of mathematical understanding, either for physical modeling or for data analysis, statistical methods for being able to analyze that data. These days, when students ask me, they want to work, one of the first things I say is, well, what computing experience do you have? Because that's essential for basically everything I do is being able to program and get the computers to do what you want. And also from the computer science side, in the sciences traditionally, at least in the physical sciences, we've worked with understanding how nature works, and we've tried to tell the computer how to do that exactly. And so we take the laws of physics, and we give instructions, and then we try to predict what should happen, the data. But increasingly, in the data sciences, people are trying methods of machine learning where they say, actually, we don't understand the physics. It's really complicated. Maybe you don't understand the biology of it. That's really complicated. And so you take the output, the data, and then you ask the computer to learn how to reproduce it. And then you study how did the computer reproduce it. And so we also have in computer sciences, some of the algorithm work in data sciences. So there's a lot of different approaches you can take. And there's classes, whether it be introductory gen ed classes to graduate level, the whole spectrum in each of those programs that can help us in the sort of decade-long search for these planets.
Great, thank you for that advice. Hopefully the student has a path forward now to eventually making it into your lab, maybe. And then the last question I have here, so if you have another one, feel free to raise it, is a question about your term curiosity-driven science. And what is that really, and how does it contrast with maybe other types of science?
Yeah, so sometimes you have a goal in mind. You say, I want to cure cancer. That's a worthy goal. That's a big goal. It'll probably take decades, just like finding planets will. And it's directed by a mission you have and you want to accomplish something. And there's good things about that. The challenge is sometimes in your rush to accomplish one thing, that maybe there's other things that get overlooked. Maybe the funding agencies prioritize curing diseases that have terrible impacts on people's lives at the expense of things that might be even as valuable 10 years down the road, but we don't appreciate it yet. And so in curiosity-driven science, we say we're not necessarily trying to solve a particular problem. We're trying to understand how does the universe work, what's out there in the universe, and answer questions that are just interesting, and ask questions that make you go, what could be out there? And you don't always know the question when you start. You conduct a survey, you learn about new types of planets, and the joke is, you make more questions than answers, right? It's a little bit of truth to that. And so in curiosity-driven science, we have the opportunity to pursue things kind of without the demands of an urgency that you might have if you were trying to meet a specific need on a schedule. And so that lends itself to sometimes a different style than research that's focused on, I need a widget for this part by next month. And you're sort of saying, how do I engineer that very well? And so there's a mix of different types of sciences, probably in every department. I suspect that many of them have a balance of both curiosity-driven and sort of application-oriented problem-solving type questions. And I think it's important that as a research university, we help expose students to both of those types of projects. So somewhere they have a real end in mind and it's clear what they're doing, but also instill in them an appreciation for learning about the unknown, for trying to understand how the universe works, and recognizing that sometimes things that seem really abstract and useless when you first learn about them turn out to have interesting applications down the road. And we certainly see that, for example, in where our graduates go, and that they go into lots of fields. Some of them I could have predicted. Other times I'm like, oh, I never thought of that. But yeah, I guess there is some overlap. And so we get to see how the students transfer that knowledge to lots of different fields. And I think that's one of the things where, in a world where we specialize increasingly, finely, and in order to be an expert in something, you kind of ignore everything else, and you become the world's expert in something when you get your PhD, but it's a sub field. Well, in order for that knowledge and skill to have impact beyond what you do, it needs to talk to somebody else. And so this sort of interdisciplinary style of research is very important for, I think, transferring the knowledge that's gained in one field to other ones.
Yeah, I love how you made that distinction between the science with a goal and science that's just curiosity-driven, and how both are important for
and I just thought of an application. Let's start here. So, for example, we wanted to be able to, when we look at a star, the star may not be perfectly centered in our field of view. And so we have to figure, how do we make sure the fact it's not centered doesn't cause the lines to appear to shift? And so they went through all sorts of contortions to develop fancy optics to be able to deal with that. And then one of the graduate students did a fun little project where they took some of the technology they developed for this scrambling process, and they stuck it in front of, I don't know, it was an iPhone or camera lens, and then used it so they could make an imager of your blood cells. And so people are interested in using this to make a sort of cost-effective technology that can be deployed in environments that don't have access to research universities' facilities to be able to diagnose some diseases that are recognizable from that type of cost-effective microscopy. And that's something that I don't know, maybe he had a plan for it, but I never would have thought of that, right? But then through the process of doing this weird stuff, you think, oh, here we have this fancy little lens that can do things. And so those are examples of applications that just come up out of nowhere, or at least seemingly out of nowhere, only after you're halfway into the project.
All right, well, that's really exciting to hear. And so I think for this last question, we're going to, it's a clarification on one of your slides as well, the one with the many orbiting planets orbiting around the suns, which are all orbiting around the solar system. One of our audience members was just asking for a little clarification about the meaning or key purpose of this and what it shows.
Right, so each of these little sort of set of circles is a planetary system that was discovered by Kepler. And so each circle or disk represents a planet orbiting, and the sort of circle it follows is its orbit. And the main thing you see here is comparing the scales, right? So the dotted lines show the orbits of Mercury, Venus, Earth, Mars. And so as you go out the planetary, our own solar system, and what you'll notice is that all these planetary systems basically fit inside, not just our solar system, but the inner parts of our solar system. And so when the Kepler mission was being designed, people thought, well, we're going to try to make it so we can find some Earth-like planets, but we didn't really anticipate that there would be so many planets so close to their star. And what do you know, when we looked, there were. And that was the great opportunity. Because those planets are so common, we're able to learn a lot more about planetary systems that are really compact and close to their star, as you can see by comparing sort of the size of these circles to the orbits of the inner planets of our own solar system.